Now it says solve using elimination. Why would it be a waste of my time to try to solve this doing substitution? Top equation. If I want to get x alone, am I going to have to divide by 2? So is that going to force me into, by 3, excuse me. Is that going to force me into having a fraction here? 2/3? And over here, 8/3? And you don't like fractions? So if you don't like fractions, why would you do that? If I want to get y alone, still got to have a fraction, aren't I? But I got a whole number over here. Still got a fraction. So I wouldn't try substitution of the top equation at all. Bottom equation, can you see the same thing? You have to divide by 2, fraction, fraction. Or you have to divide by 5, fraction, fraction. So substitution may not be the smart way to work the problem unless you like challenges. Because then you force yourself to work with a fractional value. So here, elimination. Now with elimination, we have another concern in the problem. The things that you don't like about fractions are still things that you have to have at least a basic understanding for. What you need to do here is you need to find the least common multiple for the variable that you chose. And that means that you also can make an intelligent choice of variables to choose. I would not have tried to get rid of x first in the problem. Because when I look at the y variables, the one attractive thing about them is they've already got an opposite sign sitting in there. So adding, if I can just get those to be the right coefficient in the problem, will automatically take care of my problems in the exercise. Now we're saying we don't want to have fractions, but we're using the concepts of if we had fractions, what would we do? So in other words, think of it this way. If you had a 1/2 and a 1/5 that you were being asked to add together, wouldn't you need a common denominator for those fractions? Mm-hmm. And that would have to be something that 2 divides into and that 5 divides into, the least common multiple in this particular case. So the least common multiple in this particular problem you'd probably look for would be a 10. So what you're doing is you're looking for something. Hang on a second. Something you can multiply by to make the coefficients on y the opposites. That means you're going to be transforming your equation. You're going to be changing the way your equation looks. So you've decided that you're looking for that value of your least common multiple is going to be a value of 10 if you're attacking y. So what do I have to multiply by 2 to be able to get to a 10? Top equation gets multiplied all the way across by 5. That's called a transformation, or a modification, if you will. I'm enlarging it to a status where I'll be able to add in my next step, because I'm not ready to add right now. So I come up with a 15x minus 10y is 40. Everything gets multiplied, or it's not a property of equality. It's not fair. So what am I going to do in the bottom? What do I need to multiply the 5 by to be able to get a 10?
2.
So that was going to be multiplied by 2. It's like taking two pictures and saying, I need to have these enlarged so they're both 8 by 10. Well, that doesn't mean you're enlarging both of them the same factor, because they might have been different sizes to begin with, as they obviously were. So you're not multiplying both equations by the same thing. But you're treating this problem as though you had fractions in the problem to get rid of what you don't want in the exercise. So you've already got some background skills in that. So the second equation then, modified form, becomes 4x
10y
plus 10y is equal to a negative 2. And now, isn't this a great thing to be able to see? Because that's what you wanted. You need those values to be able to cancel one another out. So this is the worst case scenario you'd have with the problem. Worst case scenario. But now if I add these two equations together, my x terms come up to give me a 19x. My y terms go away. My constant terms come up to give me a value of 38. And I have successfully eliminated one of the variables and got myself down to a simple one variable equation. If 19x is equal to 38, then does it follow that x has to be a value of 2, because you're going to divide by 19? So you have half of your answer. To find the rest of the answer, you need to take this value of 2, substitute it back into one of the two original equations.
Does it matter which one?
Nope. Here's where it gets even more, let's be smart. So I'm going to go back to one of these two equations that we have over here. I'm either going to go to 3x minus 2y equals 8, or I'm going to go to 2x plus 5y equals a negative 1. Some people pick the equation that has the nicer set of coefficients and numbers, which might make the 3, the 2, and the 8 equation more attractive. Some people like the one that has a nicer set of signs, which might make the 2, the 5, and the negative 1 equation more acceptable. It really doesn't matter, because if you're satisfying, you're going to be, in the end run, you're satisfying both equations at the same time, simultaneously. So it's got to be a 2 for the price of 1 satisfaction rate out here. Now again, most of the time, most of the problems you're going to get are going to be nice whole numbers, but not all the problems are going to be that way. So in this particular case, if I choose to take that x value of 2 back into the first equation, 3 times my x value minus 2y equals 8, where the x value is 2, takes me into 6 minus 2y equals 8. Any arguments with bringing the 6 to the other side of the problem? Leaving you minus 2y is equal to 2. Any problems with dividing both sides of the equation now by negative 2? Causing a sign change over here, and that's one of the reasons why some people stay away from equations that have negative signs in them, because they're going to have a division problem somewhere involving a negative, and we drop signs pretty easily. Simple mistakes. Or we come back over here. 2 times the x value that I'm bringing, which is 2, added to the 5y equals a negative 1. Now that means I have 4 plus 5y equals a negative 1. Any arguments with bringing the 4 to the right-hand side of the problem by subtracting 4 from both sides? Leaving us 5x being equal to a negative 1. Any problem with dividing both sides of the problem now by a value of 5? Leaving that should be a y value there, isn't it? Leaving my y value being a value of, so this is a negative 5, isn't it? Mm-hmm. That's why you were looking at me funny. I was trying to figure out what was wrong, because I know my pants aren't unzipped. Okay, so we come up with a negative 1 there. Either way we look at it, did both of the equations give us exactly the same solution for the y value? Which is comforting, because that is a way that you can check your problem. Instead of going back to the original equations doing the substitution errors, you could actually dump that into both equations, because if it gives you a different number in each cases, then there's something wrong with your input. But checking is still a viable alternative in the problem. So now it looks like our solutions turned out to be where x is going to be a value of 2, y is going to be a value of negative 1. And the vast majority of the time they ask you to enter those as an ordered pair, because they're saying you could have graphed these as well. That's about as ugly as we can get in these exercises. This was actually probably the ugliest type of problem that we could have if we're trying to solve the system by hand. This is what your number one problem on the test is going to look like, but the number one problem you're given on the test will be a problem that will work nicely for either substitution or elimination. It won't force you to do one or the other. You might have to do a little bit of manipulating signs to get what you want. So we might give you 2x plus y equals 7 and a 3x plus y equals 9. Well, now you might do some sign manipulation to be able to get to your addition problem or substitution problem, but it's going to work for you. So here, solve by substitution or solve by